So this note up here is just for the Mac users. That doesn't mean that you have to have a Mac to do the class. Module you need to install if you have installed it on a Mac in order to get rid of a warning message. So MindTap, hopefully everybody's gotten a subscription to it. You can access our course, our section for it. Under Content, go down to MindTap, click on our section. You should be prompted to log in, and if you bought your code from the bookstore, you can enter it there, or else you can buy a new account right then and there on the spot. So we are hitting chapter 1 now. So I'm going to start using the PowerPoints. You can access the PowerPoints through this interface. I'm not sure that you have the same menu option, but maybe you do. Maybe under your name, if you click on it, maybe you see something that says New Dashboard and then Original Dashboard. The new dashboard does look cleaner, so I switch to that when I go to it. And what you'll see is, a list of the chapters. If you want to read the book, go to that chapter, and then you can click Read. It's got a full screen option, so you can read the text full screen. I have not done the download your data files yet, or if I did it from the other, alrighty, data sets and video lessons. So it has its own videos that you could watch besides, watching our lectures. If you click on the Study tab, you might not be able to see it on my screen, but what you'll see are these study cards. Scripting language, executes, flip the card. What does that mean? To run means to have a computer use a written and compiled program, also called execute. And so on. And you can also add your own cards if you ever wanted to make your own study cards that way. Shuffle the deck so that you don't know in what order that the cards are coming in if you look through them. And if you go to Study Review, you get to a slideshow, PowerPoints. When I maximize them, maybe they fixed it. Yeah, it looks like they fixed it now. But previously, when I had maximized them, you wouldn't get any of these controls, these next in your previous ones. And so I got annoyed with that, and so I went and I actually got the PowerPoints from the other instructor website and installed them. So if you want to use the PowerPoints that are in our D2L website, that's cool. If you want to do the study review section under MindTap, that's also cool. I'm going to go ahead and grab the PowerPoints grab the first PowerPoint from D2L itself. So under Content, PowerPoints. Whenever you click on something in D2L and it pops up in the little preview window, especially if it's a PowerPoint, something with a lot of pages, you want to download it rather than just view it in the preview here. So that's what I'm going to do. Scroll down to the bottom, quick download. An overview of computers and programming. So we're going to learn about computer systems, simple program logic. This stuff sounds good. The steps involved in a program development cycle. Pseudocode and flowchart symbols. And as we go along, we are going to start doing some flowcharting, and I have some kind of styles that I like for people to follow. Kind of a certain flowcharting grammar. However, if you use the ones that are in the book, I'm not going to count off for that, but I will show you what I'm expecting as well. So I just have kind of a cleaned up version that I like for people to follow, and you'll see what I mean when we get there. So what is a computer system? It's a combination of all the components required to process and store data using a computer. What is the hardware? It's everything you can pick up, the equipment associated with the computer. What is software? Software instructions that tell the hardware what to do. And so, you know, last Wednesday I wrote the dude in the box, and we kept giving him a list of instructions. The list of instructions are the programs that you write in order to get the processor to do something. So the programs are the instructions written by programmers. That's kind of tautological there. Programming is writing software instructions. What you have to do is you have to have, well, we'll get to that. This is a little too basic or a little too bullet pointy-esque. We'll roll it for just a little bit more. So applications. Applications are considered your things that either, you know, make you money or give you entertainment. You know, word processing, spreadsheets, you know, any kind of business application, or your games, things like that. Those are called applications. You know, if you have something that manages your hard drive, you may think that's fun, but probably nobody else is going to really be that entertained by it. So there are utility programs as well. System software is the operating system that you know, that drives your computer. iOS for our iPhones, Android, you know, Windows, Linux, Macintosh. All of those are system software, the operating systems. So what do you do with your computer? You do several different things. Largely, you get input, you do some processing, and then you do some output. That's even the way games work, right? You have your joystick, that's the input. You move your joystick, gets processed, and then the output is displayed in the form of, you know, a new frame of data on the screen. And then again, you know, you're moving. It continues to do that. It's responding to your input. It's gathering input. Now, we're not going to write games that, you know, respond to joystick behavior and stuff like that. But our concepts are the same. We will be entering input. It will do some processing. It will display some output. And one thing that happens is that after people have written a little program, you don't have to do this, but I'm going to load up idle and try to get to the program that we wrote last week. So what I did is I typed idle, and I'm going to go File, Recent Files, and then I found my old program. So if I do this, if I run the program, what is your age? People get frustrated because they want to keep running it, right? Well, what's it doing? It's not running my program anymore. You're right, it's not running your program. What's happened is once it got to the end of the program, as far as it was concerned, it was all done. And now you're just left in the shell, not doing anything. And yeah, you could type in numbers and stuff, but it's not going to do anything anymore. So if you wanted a program to let you continue to do things after the first input, you have to write it in such a way that it will continue to do things after the first input. You have to write in what's known as a loop. And we'll learn about looping. Another thing I need to point out is, and I don't think that I did this last Monday, if you come and you find your PY file and you double click on it through the user interface, through Windows, rather than running it from within idle, here's what happens. Okay, cool. What's your age? Great, I'm running my program, 45. Oh. It closes it immediately. We don't get to see the results. So if you want to write your programs in such a way that they can be executed by double clicking on the icon, then there's an additional step you need to do to your programs in order to get them to pause at the end so that people can see the input, the output. And so on my code, and we'll do this again when we write our next program, if I change that word print done into something like input or something like that, then it'll wait for input. So that, and I hit Control S to save it. Again, you don't have to be doing all this. We're not actually writing a program. I'm just demonstrating. If I run it through the Windows user interface now, when I'm done, there, right? So that way it hangs around rather than closing it immediately. And then if I hit enter, it does go away. So that is a trick you can use in order to stop your programs from closing the window as soon as it hits the end of the program, which is to ask the user for one more bit of input, but they don't even know you're asking for input, right? It just says done. Or we could have said press any key to continue, that kind of thing. You've seen that message in old programs. Press any key to continue. So what kind of input can we have? We can have text input, numbers. You can hook a scanner up or a camera and get images in. You can get sound. It blows me away that, you can tell, Siri or launch Shazam or SoundHound or whatever, and they can identify the sound, the music that is playing in the background. It just blows me away that they can do that. So processing is calculations and comparisons performed by the little man in the box, the CPU. And then your output is resulting information. Sent to the printer? We don't print that much. To a monitor? Yeah. Or storage devices? Sure. That means that after you write some calculations, you process some data, you might want to save it to file. We're going to learn how to do that. We're going to learn how to write our programs so that they can write to a disk file. Because otherwise, once the computer shut off, you lose your memory. There's nothing there. You've lost your data. So a programming language is used to write instructions using programming code. And we are going to learn a programming language in here, but there are a lot more programming languages. Now, when I was showing the series of instructions we were giving Chip, they were just opcodes. We're going to do instruction 1, we're going to read from memory position 7, and we're going to write it to this registry. Or we're going to add these two registries together. That's not how you really want to write Call of Duty. That's way too fine detail. That's called a low-level programming language. Machine language. Machine languages are languages that are written. They're just a series of numbers that control the chip inside the computer. And we don't really want to write in machine language. And a low-level language is something that turns very cleanly into machine language. Instead, we want to use what are known as high-level languages. And I'll give you a quick comparison of a low-level language versus a high-level language. All right. So, you could have a machine language dedicated to controlling the state of a light bulb. And they would have a whole bunch of different opcodes, machine instructions. And then there would need to be a way to send to the light bulb controller a series of numbers. If you send it a 1, and then turn it fully on. If you send it a 10, hey, this isn't binary counting. Turn the bulb fully off. Dim the bulb a little. Brighten the bulb a little. If it's fully on, skip. If it's fully off, skip. Go back to the start of the program. So you could write a program to control a light bulb using all those different things. They're just numbers. You wouldn't want to really write your code using numbers, but that's what people did in the 50s, you know, when 40s and the 50s, when computers were just being invented, devised. Is you would have hardware, whether it was, you know, electronic hardware, you know, vacuum tubes or whatever, and so you would want the ability to write something. I want to get a better example of machine language than that if I possibly can. And here's one for something to do with motors. Opcodes. Jump past the sensor in constant locations. Store the motor off constant here. Load the sensor value into register 2. Subtract from, you know, so you don't really want to have to write in that kind of stuff. You'd rather write in something that, you know, is easier to understand. And the first thing that people did is they just turned the opcodes into words, right? So you didn't have to memorize that code number 0010 meant load. Instead, you could use the word load. And so effectively, the lowest level programming language you can get that's not machine code, that's not pure numbers, is known as assembly. And it just has these words, which these words correspond with operation codes that the chip can perform. And so here's a program written in an assembly language for a specific kind of chip, or a specific kind of operating system for Linux. And we can see it's got words like move, move. It's just moving data around from place to place. It has some registers in it. Remember I said that the little guy had some paper to write on called registers. He's storing some values in some registers, and then he performs what's known as a hardware interrupt. A hardware interrupt is something that tells the rest of the system that it's going to go and start doing something now. So it executes a call to the kernel, the Linux kernel, in order to do this, which is to display some text. So do we need to know how to know all of this? No. But you have to see that at least we were getting to write, you know, using these little abbreviations and stuff like that. It wasn't just pure streams of numbers. That is a low-level programming language. That is assembly. We're going to use a high-level language. We're going to use Python, but there are many other ones. Typically, the first day in a class, you come in and you write a program that says hello world. I didn't do that, but surely you will in another one. So here's how to say hello world if you are learning how to program in, it's not letting me zoom in and out, thanks. How about letting me hit a class where, alrighty, so trace, hello world. That's how you would do it in ActionScript if you're writing a Flash game. All sorts of languages. This particular file has like 700 different languages in it. How to print hello world in another language. This is a very, very machine language style, but you know, it's got logic words, end message, if message. Yeah. This is a lot of work to have to go through just to print a message. This would be the low-level version on that platform, and then here's the high-level version. Print hello world. I would much rather do that than to do this low-level assembler version that is shown below, right? I'd rather be able to just say print hello world. Eventually, at some point, this print hello world has to be turned into the zeros and the ones that run the chip. And that act is called compiling. What happens is we have some English-like programming words here, and then something has to turn them into machine language. So something's got to go and translate what we have typed here into the operation codes that will actually drive the computer to do stuff. If we looked up and down, we'd find the one for Python, and it's just a print statement. Yeah, like that. Print hello world. There we go. Yeah. So there are lots of different programming languages. Visual Basic, C#, C++, Java. The C syntax feeds whole bunch of different programming languages. They were all developed, using a common syntax because the C syntax was clear and easy to understand. And a lot of people learned it, and then they took that knowledge when they went to other programming languages. Python does not follow the C syntax, but we'll see examples of code in this text that are written in C++ or Java, and they're not too difficult for y'all to understand. And then later on, you can go and you can take the C++ class that we offer here, or Java, and you'll learn another language. Just by learning one language doesn't mean you know everything there is to know about programming, but it's like learning to speak Italian. Once you learn how to speak Italian, it's easier to learn how to speak another Romance language because the syntax is very similar. So computer memory, the internal storage, random access memory. It's called random access because it doesn't have to be accessed in order, right? Like a tape drive. Imagine the old days of the tape drives. You had to read that instruction, and you had to read that place, and you had to read that place, and you had to read that place. But if it's random access, you can tell the computer, okay, get the value at location 1000, and then get the value at location 10, and then write to the location at 2000. So that's what random access means, random access memory. A lot of the memory in our computer is volatile memory, meaning that it's erased when the power is off. It seems like with our phones and stuff like that, doesn't feel like memory is getting erased at any point because, they're always on as long as you're keeping it charged. But eventually you may have a need to reboot your phone or your battery runs out or whatever, and then all the programs are going to have to be loaded again fresh the next time you launch your phone. So volatile memory, this is why we need the ability to write things to a more permanent storage, to write things to a file, is because otherwise when the program ends, then your calculations are turned off. It'd be a real drag if you were a data entry person typing in, statistics, census data for Oklahoma City, and then as soon as you entered all 7 million records, you turned your computer off and it was gone, and the next time you wanted to run a report, you had to type in 7 million records again. You wouldn't want to do that. So permanent storage devices, hard drives, floppy drives. Nobody uses that kind of stuff anymore. Well, our big desktop computers still have hard drives in them and stuff like that. But non-volatile memory is memory that retains its state when the power is turned off. You could have non-volatile memory. The crudest form of it was punch cards, like in the 50s and the 60s. It's just a card, that hole's been punched into. Well, that's sure non-volatile because if you turn the power off to that card, it's still got its holes punched into it. But for the longest time, magnetic media was the non-volatile memory of choice because you could get it down very dense. Hard drives still work on this idea. A hard drive is essentially just a magnetic platter that's spinning very rapidly with little heads that can read, and if the read and write to it, and if the spots on the magnetic strip are written to in a certain way, it means it's a 0, and if they're written to in another way, it means it's a 1. But you turn your power off to your hard drive, those magnetic spots on the spinning platter maintain their charge, and there are floppy disks, that people wrote, wrote to in the 70s, and that can still be read because the magnetic data maintains its state for a long time. If that wasn't the case, if magnetic recording tape didn't keep its its charge, then all the recordings done by Elvis and the Beatles and stuff like that would all be gone. But there are magnetic tape recordings, not computer recordings, going back to the 30s or whenever it was first invented. So non-volatile memory nowadays is usually like flash RAM. People use the hardware version rather than the spinning disk versions. And your phone's got both kinds built in. It's got volatile memory and it's got non-volatile memory. So my phone's got a gigabyte of RAM, and it's got 128 gigs of the other kind. Well, the RAM is the volatile memory that gets wiped out when you turn it off, and the rest of it, where you store your apps and your pictures and your songs or whatever, is the non-volatile memory. So the compiler or the interpreter takes your source code and converts it into machine language, into the binary numbers. And while it does that, it checks for syntax errors. If your program has syntax errors, it's not going to run. It can't be compiled. It can't be interpreted. once your program has been compiled, your code has been compiled or interpreted, then you can run it or execute it. Input will be accepted, processing will occur, and results will be output. Now, not every program will have input, right? You could just write a program that prints hello and then it quits. That is a program, just not one that accepts input. The vast majority of time, though, people want programs that actually do, have some input. They have some control over the program. Like the difference between a game and a screensaver, right? The screensaver just comes up and it displays stuff, but a game, responds to your commands. So I'm going to kind of break this out into some separate notes here. But there's several different kinds of errors that you can run into when you're programming. And I'm going to break them into 3 categories here, although this slide does not do the same. At a certain point, I'll call this out and say, I want you to be able to answer this on a quiz question or that kind of thing. But for right now, there are errors which could be syntax errors. Syntax errors are just a problem with the grammar. I shouldn't say just, because they can be annoying to fix. But, if you have the word print, but you misspell it, right? It's not going to be able to convert that to, it's not going to be able to compile or to, to process that. And so the program will not run. So syntax errors are effectively typos, mistakes in the grammar of the language, that kind of thing. Meaning that the code cannot be compiled, translated. Then there are logic errors. Some textbooks call them semantic errors. Logic errors are when the typos aren't there, but it gives you the wrong answer. It does the wrong thing. Like if you were supposed to write something that would show that somebody had a fever if their temperature got above, a certain value. And instead, it was always showing that somebody had a fever every time they had a temperature below 97 degrees. You have a temperature of 96, okay, he has a fever, call the doctor. No, that's a logic error. The logic error is, because the code was written in the wrong way. I think we demonstrated that just a little bit in that program that we wrote last Monday, where I was checking to see if it was less than 17 rather than less than 18. That's a logic error. It runs, it just doesn't produce the right output because of mistakes in the logic. So, program runs, but doesn't run correctly due to mistakes in the program's logic. And then there's a third kind that this slide did not mention. This slide mentions syntax errors and logical errors, but runtime errors. Runtime errors are when the program's running right, but then something happens that stops it from running. You're driving to Walmart, but you blow a tire. It's not your car's fault that the tire blew, right? It's not a syntax error. It's not a logic error. It's just something happened that prevented your car from making any further progress. At runtime, the program is running, and due to a state that the program cannot predict, it stops running. Common example of that is, what if you need to save data to a hard drive, but the drive is full? Drive is full. You can't write to it. Well, that doesn't happen all that much anymore because people have, terabytes of information on their hard drives, but still. Or it needs to open a file, but the file name does not exist. Or it needs to access a website, and the website's down, your internet's down, Those are all examples of runtime errors. So the program is halted when it reaches an unexpected state. Part of learning how to program well is to learn how to accommodate runtime errors. You don't want your program to crash just because the internet cannot be reached, right? You instead want it to sit there and wait and to try it again, or to display an error message and then let the user try to reload the document, that kind of thing. So you will learn how to deal with runtime errors as you become a better programmer. File doesn't exist, well, prompt the user for a different file name or offer to create the file for them. So, part of programming is writing a program to handle runtime errors. And handle can be just let the user know gracefully that something is wrong and quit. That's kind of the worst kind of handling. Or to let them take steps to correct the issue. Click OK to reload, that kind of thing. So the logic of the computer program is a sequence of instructions in specific order. Like if you're going to bake a cake, there will be a series of instructions that you have to follow. That is the program for baking a cake. More officially, it's the algorithm for baking the cake. Take 2 eggs, take 1 bag of flour, take 10 pounds of sugar. Mix in bowl, throw bowl in oven, cook for 20 minutes, throw away. Okay, there's my algorithm for making a cake. It's a horrible one. It's not a good one, but it's the logic. Take 2 of this, take 3 of that, cook at this certain amount of time. If not warm, continue to cook, that kind of thing. So we will write programs using logic. Logic is just the sequence of instructions in the order that they need to run in order to produce the output that we want. So when we had Chip reading and writing, from the memory into the memory, we'd say read location 800 and write to memory location 900 and stuff like that. It's easier if we can give those memory locations names. And so what is a variable? It's a location in memory with a name. If we look in that code that we wrote, age. Age is a variable. You can give your variables almost any name that you want. There are a couple of rules for variables. So a variable is a named location in memory. They typically have, or I shouldn't say typically, this is how I define them. The book kind of comes up on it and doesn't quite do it exactly the way I would. They have 3 parts. They have a name, they have a type, and a value. The type is what type of data the variable is holding. If I do this, age is equal to 10, we know what the name of it is. We know what the value is. But that 10 has to be stored in the computer's memory, and it is being stored as what's known as an int, int, an integer. Are you just supposed to look at it and go, oh, well, I know that a 10 is an int? Well, not yet, but you will. An int, an integer, is a whole number. So 10.5 would not be an int. If you're ever curious about what kind of data something is, you can launch Python. Go to the shell, Python shell, and then if you do the word type, T-Y-P-E, parentheses, and then you give it some data, it'll tell you what it is. Well, a 10 is a int, integer. How about if we added a decimal point to it, 10.0? That's a float, floating point. It means it's got a decimal in it. What if it had quotes around it, like type 10, like that? That's a string. A string is just a series of letters. A string isn't a number. Behind the scenes, it's a series of numbers that's written out, but it's just a string of characters. Anything you can type on your keyboard is known as a string. And in this language, Python, usually when the user types something in, we have to convert it from being a string to being a number. Because you can't do math on a string, because a string could be anything. It could be my name, Thompson. I can't say Thompson plus 3. What does that mean? So instead, it has to be converted into a number before we can do math on it. And in our code on Monday, we did that. This converted it from a string to being an integer. So let's write these data types out. An int is an integer. It's a whole number. No decimal point, right? Can I type? Yes, I can. There we go. And then a float is floating point, means it has a decimal number, decimal in it. And then a string is a series of characters. So if we had some examples. Is that one an int, a float, or a string? Well, are there any decimal points in that one? No, so it's not a float. We're going to say that it's an int. It's a whole number. What about that one? That is a float. It's got a decimal point. This is a string. We're going to say that it's a string because it's got quotes around it. In our programming language, if it's got single or double quotes around it, it's being interpreted as a string. So that's an int. No decimals there. That's a float. And this, it looks like it's a number, but it's got the string, the quotation marks on it, so it is in fact a string. And if our program had this data stored in it and it wanted to do some math with it, it would have to be converted. So in Python, and in most languages, data from a string must be converted. To an int or a float before math can be done with it. So in Python, the input function returns a string. So when our program did this, when our program did print what is your age is equal to input, this lets the user type in stuff using a keyboard. The result is stored in the variable named age, but that stuff that it's holding is a string because we don't really know what they typed. We don't know if they typed in 18 or if they typed in, you know, I love Star Wars. We have no idea what they typed at that point. It has to be converted into a format that the computer understands as being a number. And so that's what this next call does. This gets the input, stores it in a variable, but the input, I'm going to put a comment here, age contains a string after this. And this converts the string to an int. Did we have to use the same word as we did there? No, we could have stored it in something else. You can do things like this. No, I'm not going to even go into doing things. So now age at this point has been converted into an int and we can do math on it. So that's what the next line is it's doing a comparison. It's taking that number and checking to see if it's less than 18. If it was a string, if it was I love Star Wars, could we see if I love Star Wars is less than 18? No. If they type in something that the computer's not expecting to be a number, but we told it to be converted to an int, we will get an error. If I run this program again and I type in something other than a number, I'm going to get a runtime error. Runtime error, the program was not expecting me to type in words when I wanted numbers, and so it blew up, it crashed. If you get an error like that and you're trying to fix your program, it does give you some information about it. For one thing, it tells you the line number. It says it happened in line number 4. That'll usually let you zero in on where the problem is going wrong, where the problem is. we could go back to our code. We have to find line number 4. Unfortunately, there are no line numbers down the side like you may have seen in some programming languages. But if you look down here, it says line number 4 at the bottom. And so if you move your cursor up and down, you'll see, okay, line number 4. And then you'll look at this and you'll compare it to the error message. The error message was invalid literal for int with base 10. And you go, what? It takes a while to understand the language that it is speaking when it is telling you these errors. Invalid literal for int. You finally go, oh, okay, I typed in something that's not an integer. That's what happened. And so there are ways to check for that. There are ways to accommodate for that. We're not going to worry about them at the beginning. At the beginning, if it's the user's fault that they typed in something wrong, we're not going to fix it. But then as we go along, we're going to learn how to fix it because we don't want our programs to crash with a red message just because they typed in something wrong. What if they were trying to type in 10, but they accidentally typed in 1, 0 rather than a 0? Yeah. Is it fair to just kill the program and stop running because they made that mistake? No. We should display a message and then let them type it in again. So the input function returns a string which will need to be converted if it is to be used as a float or an int. So if we were going to get some input from the user, I'm going to write 2 little short snippets of code. One is to do this, print, enter your age, and the next line says age is equal to input. That's one way to do it. And then we'd need to convert it to an integer. Okay. We could shorten that because in this language, not in every language, the input statement can have the ability to specify what the message the user sees. You could do this, age is equal to input, like that. That takes the place of both of those lines. Now I'm converting things to int with that int just because I was kind of not expecting the user to want to say that they were 18.0 years old. But really, for the most part, we ought to be converting them to floating point numbers because what if they did type the decimal? You know, I might not expect if I ask somebody's weight to enter, 180.1, but if they happen to know that 0.1, they may want to enter it. So really, throughout the rest of the course, I'm probably going to be changing things to floats rather than ints as soon as they type them in. So I'm going to change my 2 little examples there. And if I change that in my code here, it would work just as well. Because you can compare, 18.0 against 18 or 16.3 against 18. It would work just as fine if this word here was float as if it had been int. So the input statement can be, I will kind of waffle between using these 2 different things. Is it easier to type it like that because it's just one statement rather than 2? Yeah. There's one more visible side effect from doing it this way rather than this way, and I'll try to demonstrate it. If I run this code as is, where I do the prints and then I do the input, notice that my cursor is put on the next line, and that's where I type in stuff. However, if I had put that message here inside the input statement, by the way, if I enter a hashtag in front of it, that's called a comment, and it means that everything after the pound sign, after the hashtag, is ignored by the code. And so the editor reads it all out to show that it's not actually part of the program anymore. So This is called commenting a line out. It means I wanted to leave that code there maybe, but I don't want it to actually to have any effect. So I've just commented it out. Now that I run it, now that the text is inside the input statement, right? It says, what is your age? But the cursor is right there on the same line. If you like that, and I kind of do, you might want to do it that way. So I hope you saw the difference. The first time when we printed it and then we did the input, it displayed what is your age and the cursor was underneath it, waiting to be typed in. The next time we did it, we had the text message inside the input statement, and so it printed that message out, and then the input was going to take place right there on the same line. So the variable, it has a name, it has data, and it has a type. In this particular language, we don't have to specify the type of the variables. In some languages, you do. In some languages, if you knew that age was going to hold a number, before you used it, you would have to do this, int age, or float age, or string name. You'd have to specify them before. Those are called strictly typed languages, or strongly typed language. Python and JavaScript and a lot of other languages are not strongly typed. You do not have to declare your variable before you use them, and you don't give them a type. The type is determined by what is being given to the variable. And since input always returns a string, then at this point age is a string. And then this function turns it into a float. So it can change on the fly depending on what you tell it it's going to be, but you don't have to specify beforehand what the type is. So a development cycle, you have to understand the problem, you have to plan the logic, you code the program, you use software, a compiler or an interpreter, to translate the program into machine language. You test the program, you put the program into production. Now, is it that easy? Does it just follow 6 steps? No, usually not. If you're working in a business environment or whatever, you will negotiate with the person who's writing the requirements of the program in order to understand the logic and understand the problem and to plan the logic. You will be given requirements, and you will need to write the requirements out, and you'll show them back to them, and they go, okay, yes, that works great. And quite often the people who are writing the requirements are not the programmers themselves, and then the programmers can plan the logic for it. So anyways, you have to understand the problem, you plan it, and then you code the program. These are kind of circular steps. You keep writing, you keep writing, you keep writing, you fix the bugs in it, you keep writing, you fix the bugs. Yeah, and so then you test the program, and it turns out there was a problem with the logic. So you revise it, you compile it again, you test the program, you find another logic bug, and then finally you think the program meets all the requirements and doesn't have bugs in it, and so you put it into production, you ship it to a user, you publish it on the App Store, whatever. They find bugs in it, and so you have to start that little looping process again, where you try to identify the cause of the problem that they found, fix it, and then redistribute it. So it's often illustrated like this. Understand the problem, plan the logic, write the code, translate the code. That's not our step. The computer does that for us, the programming language does. Test the program, put the program into production, maintain the program. Is it that easy? No, it's usually you get stuck in this loop, and then you get stuck in this loop, and then you put it into production, somebody finds a problem, it goes back, so, there are all these, whorls going along in it. But as the listed cycle, development cycle, that's one way to put it, yeah. You get your requirements, you develop the logic, you write your code, you test your code. Understanding the problem. One of the most difficult aspects of programming, the users are the people for whom a program is written. And then the documentation is all the paperwork for a program. Does anybody really use paper? No, but documentation consists of instructions on how to use the program. It also consists of comments that are added to the programming code itself. Remember I said that red line stuff? I can put some comments in here and it would serve as documentation. So this was the Air Force Enlistment Program, written by J. Thompson, January 2018, 9. Well, yeah, 8. That's what year we were in. Then, what does this do? Asks the user for their age and prints a message saying whether they are too young or not, right? Okay, so now I've added some comments to my program. I'm going to want you to do something similar to this for every homework assignment program that you write for me. Everything you need to turn in, everything you turn in needs to have some comments at the top saying what the program is. And at the very least, assignment 7, in your name. Just show that you know how to add comments to it. But if you put a description of the problem, this program converts Celsius to temperature. This program calculates the user's BMI based on their weight and their height. That kind of stuff. You put some comment up there at the top saying what it does. This is called a code block or a comment block. You just describe what the program does. That's not the only place that you put comments in a program, though. You can put comments all the way through your program. Like these 2 lines of code. What did they do? Get the user's age. And then determine if they are too young, or indicate if they are too young, right? So this is like writing the outline for an English paper. The comments are like the outline. You can go and you can add the comments first, and then you can come back and fill them in with some actual code. Get the user's age, determine if they're too young. Yeah, you have to flesh out, You could put some more comments about what's going on here. If the user is less than 18, they cannot enlist, that kind of stuff. So that's the purpose of adding comments. It makes your code documented. Makes it easier for someone to understand. And you can't go too far. You don't need to write one comment for every line of code. In old programming languages like assembler, yeah, it was actually a good idea to do that. People have published the code for the computers inside the Apollo, spacecraft that went to the moon and landed on the moon. And every single line of code is commented because the code it was that important for them, right? But when you're using a higher level language where several things happen with a single call, you don't need to do that nearly as much. But you do need to do that. Professional programmers do comment their code, because if you come and look at your code again a couple of years later after you've written it and you haven't commented it, it's going to be very hard for you to understand what you were doing. All this stuff that we write here looks easy to understand, but that's because, it's like day one programming. As you get to be more of a sophisticated programmer, the code that you write is not going to be so easy to read. And if you give it to somebody else to maintain, they're going to have a problem with it. If you need to fix it later, there are people who just write gaming engines, graphic engines that are used by other companies, so that, Electronic Arts, if they want to write, the Star Wars Battlefront game, they don't have to start from the ground up. They already have a gaming engine, graphics engine that they can then go and they can modify for that particular game. So you can be sure that they have lots of documentation about it, how to use it. But not only that, the code itself has got lots and lots of comments in it. Why? Because if something goes wrong, somebody's going to have to go in there and fix it. And if they can't figure out what's wrong, if it takes you a week to fix a bug, and it would have only taken you, an hour to fix that bug if the code had been adequately commented. The little bit of effort that you put in at the beginning of the process will save big time as you go along. And again, if you're working with a team of people, it's extremely important to comment, to document your code. If you're working in a company, they may have requirements about it. It's just a professional thing to do. But when you're sitting here doing your homework, it's probably not the first thing to occur to you. I better put my comments in there. But do think in those terms. Do think in the terms of, I want to grow up to be a professional programmer, or at least I want to write my code as well as I can to be as easy to understand. If you put your comments in there, then I understand what your code is doing, and I know that you understood what your program is doing. And so that's one of the things that I look for. If your program doesn't do what it's supposed to do, but it is well commented and I get an idea of that you knew what you were trying to do, then you're going to get more credit than if it doesn't do what it's supposed to do and there are no comments in it. So planning the logic. Plan the steps of the program and what they include. The algorithm is the recipe for solving the problem. It's the sequence of steps or rules that you follow to solve a problem. Planning tools include flowcharts and pseudocode. Desk checking is walking through a program's logic on paper before you actually write the program. So you'll have some pseudocode or you'll have some flowchart, and then you'll try to figure out if it's accurate. Why you don't want to take the time to write it in code if you can spot a problem in it, right? Just straight from the get-go. The earlier that you spot and identify a problem, the less expensive it is. When is the right time to find a problem? Is it before the program has been written? Is it after the program is in development? Is it after the program has done development and been put in all the app stores? You know, in terms of expense and fixing, you know, if you can fix something at the beginning of the process, that's far more, you know, that's the best place to catch it. The worst place is when it blows up in the user's hands. So coding the program, hundreds of programming languages are available. The vast majority of languages, you know, they're all built on similar concepts. Loops, variables, and calculations, you know, input, output, and things like that. But there are different languages that are based on different programming paradigms. You choose them based on the features. Coding is easier than the planning step. Experienced programmers can successfully combine logic planning and program coding in one step. I'm not sure if that's an accurate statement, but yeah. So, a lot of people just want to sit down and then start typing code without having done the pseudocode or the flowcharts or whatever. And sure, you can get away with doing that, but if you have some design up front, and if you're writing this program for somebody else, then you can work out errors in it before you actually start coding it. So using software to translate the program into machine language. So you keep using these two terms, compiler or interpreter, compiler or interpreter, compiler or interpreter. At this point, I'm just going to use the word compiler from now on. And then we'll get back to what the difference between an interpreter and a compiler is. But something has to translate the English-like high-level language into the low-level machine language. Something has to turn those words, print and input and stuff, into the series of opcodes that actually control the hardware underneath. And so when I write my program and I'm ready to run it, I press run, run module, and then a program comes through and it checks all of the syntax and it builds the machine language for the chip to follow. It compiles the code. So I run the module. If there was a mistake in it, like I misspelled the word, well, like I had too many parentheses, something like that, then it's not going to compile. It says syntax error, invalid syntax. That's a mistake in the grammar where it just cannot continue. Now, annoyingly, the line that it highlights is often not the line with the error in it, right? If you hadn't seen me make the change that caused that problem, then you could stare a long time wondering what was wrong with this line. And there is nothing wrong with this line. But that's the line that I highlighted when it said that there was an error. The problem is really that it's missing, you know, that I added too many parentheses there. So debugging, spotting your syntax errors can be hard. And that's why I take the time to wander around when we're typing in our code. And, you know, I know that people get stuck. And if you're done with your code and you can look over the person's, you know, your neighbor's shoulder and go, okay, well, look, you have two parentheses there and you made it just one, and that kind of thing, then it can help speed up the progress of the class. And it's not that it's trying to be deliberately perverse, by showing us the wrong line number. It's just that it couldn't figure out that it was wrong until it got to that point. Whatever little indicators it's looking for to build up the logic of this code went completely off the rails at this point. The problem was introduced as far as it was concerned here, but it didn't break the language completely until it got here. So whenever you see an error in your code, you're shown an error in your code, or you're shown a line number when you run it and you get a runtime error, and you can't spot the problem on that line that it highlights, go and look at the line of code above it and see if you can spot it there. So if I was wandering around and we looked at it and we saw that that line wasn't working, then I'd say, okay, is there something wrong in that line? And then if you looked at it and you go, I'd point at the extra parentheses or whatever. So you just have to kind of get used to the fact that it'll try to show you the error, but sometimes you have to look up, find the the error in the preceding line or lines. So a syntax. It's a misuse of a language's grammar rules. That sounds harsh. I misused the grammar rules. I think of it as a mistake rather than a misuse, but I guess that technically that's a correct definition. So it's a mistake in following the grammar of the program, or it's a typo. You put in, a period where there needed to be a comment, a comma. You typed in a variable name using capital letters in one place and lowercase letters in another, or you misspelled it, or you put a capital letter, at the beginning of the word, and then later on you didn't use that capital at the beginning of the word. You just have to make all the variable names match, all the function names correct, make sure that all the punctuation, the parentheses, and the commas, and the periods, and whatever that the program needs are correct. So the programmer needs to correct the syntax errors. You might need to compile the code several times. That's optimistic. Might need to compile it hundreds of times. If you're writing a long program, my advice is compile early, compile often. Run your program as you write it. Don't write 100 lines of code and then run it and start trying to figure out what was wrong. You should have run it after the first 10 lines of code that you wrote. Every time I make a change to a program, I go ahead and rerun it. Now, so especially in a class like this where, we're just typing in short programs or whatever, it's not a bad idea to save your program and run it after every few things that you type. The earlier you catch your problems, the better off you are. So you write and correct the program code. You compile it, you run it. If there were syntax errors, you will get a list of error messages. You will correct your program code. You compile it again, you try to run it again. If you still see syntax errors, you keep doing that until you don't get any more syntax errors. If it runs, then when it runs, you get some program output. The data that the program uses is fed in to the program, and you get your output from your program. So a logical error. It's when the syntax is correct, but the logic is wrong. If age is greater than 18, tell them to go enlist. No, that's the wrong logic. So testing. You execute the program with some sample data to see whether the results are logically correct. And you don't only want to test to see if your program works, you also want to see if you can break your program, because if you can't figure out how to break your program, your users certainly are going to. And so there's often a test department at a company that tests the software to make sure that it's good. Because if you send, if you write something and then you send it out to the government and they're running and they're using their program and it blows up every time and they type in an O instead of a 0, they're going to be quite irate. And it's a very expensive process. You need to make sure that your code is as problem-free as possible before you do distribute it to somebody else. Debugging is a process of finding and correcting programming errors. Programs should be tested with many sets of data. Generally, you want to test your program every, it's like streams that branch, you have all these different branches of logic, these if statements and stuff like that. You need to test what happens if you enter good data, if you enter bad data, find out those boundary points between the good data and the bad data. So you do have to test with multiple sets of data. You need to try your program. Don't just run it one time and then go, okay, good, it worked. It can take several months to do all of this. If it's a large program, it certainly can. Conversion, the entire set of actions an organization must take to switch over to using a new program or a set of programs. Okay, we're yanking all the Macs out of our department, and so we're going to have to rewrite all this stuff to run in C or you know, on Windows or something like that. Or we're getting rid of our accounting program, and so we have to. That's completely out of the bailiwick of learning how to program. That's more of an organizational thing. Maintaining the program. That's making changes after the program is put into production. You have the world's greatest accounting system, but then somebody figures out that there's going to be new tax laws coming up. So you've got to maintain your program. You got to go back and you need to make the necessary changes for it. That's a common first programming job is in software maintenance, where you're part of a team that's maintaining stuff that other people have written. It's a good way to learn. I've done it, certainly. So you're maintaining previously written programs. It's about time to end our lecture. You make changes to existence programming assignments, programs, which repeats the development cycle. All right, so go ahead and read chapter 1. You ought to be able to get to it through MindTap. If you're having problems accessing MindTap, let me know. There's not a lot I can do, but I can try to get some help to you. If it's just because you haven't bought it, well, you need to go ahead and get the access code for it. Alrighty, guys. That's your homework. I'm not going to give you all any written homework, but please do read chapter 1. I'd like to be able to walk through that pretty quickly at this point. We've already talked about a lot of the good stuff in it.
Since I got the book to do with Candace, I can still read online because I'm about it online, but I didn't make the MindTap.
Yeah. When you buy it, you ought to be able to get MindTap access to it. If you have a physical book, you'll have to buy the MindTap access for a little bit more. But if you don't have the book, you just do the MindTap and you read it that way.
Is it free?
Thank you.
Or like,
MindTap costs $80.
all right.
Yeah.
So I'm trying to buy it, but it's like having an error.
Okay.
I can show you what it's doing.
Yeah. I'd like to see what it's
Okay.
doing. Yes, sir.
Just a quick question.
Uh-huh.
The last day to enroll is Friday, right? Is it like this course, I'm guessing? Because my friend wants to join the classes.
Well, I thought it was last Friday.
Yeah, that's what I meant. last Friday, sorry, yeah.
Right.
So,
Right, so he would need to talk to the advisor here, and, they might let him in late. I had the lecture video so that they can catch up, so he just needs to talk to the advisor.
Thank you.
Yeah, sure.
On the MindTap, it gives you like 2 weeks or something like that of free trial.
Right.
Because I signed up for that, and for the textbook, it only gives me the beginning acknowledgments, and then give me a chapter. Is that correct? Or am I doing something wrong?
I've never used the demo version of it like
Oh,
that.
okay.
So if you want to have it on screen so I can look at it and see it with your eyes, that would be cool.
Okay, I mean, I can put more. You got a second? Well,
Yeah, I need to help her as well,
Oh,
so
yeah,
let's
go
do
ahead.
two
Why you do
people.
that?
Yeah, why you got all get locked in?
So I click pay online, and it does that.